What's up, guys? Yeah, so today I want to introduce this Minkowski inequality, and basically some also famous in the real analysis. So let me just quickly dive into. And the Minkowski inequality based on another inequality called the Holder's inequality. And if you haven't seen the Holder's inequality, then I will post my inequality list, video list that contains a lot of inequalities proof that you can go to check out. Okay. So let me just write down the first version that I want to prove, which is a discrete version. Hope you guys subscribe to my channel. Okay, so let's consider p greater than 1. Yeah, okay. So p is some integer. Okay, so greater than 1. And summation ak plus bk. Okay, so any number that I write in this video, ak, bk are all a real number. Okay, so you take you summation everything, and then for each term you take the p roots. Take p power and 1 over p. Well, less or equal to akp. Summation k 1 over p plus summation k bk p 1 over p. Okay, so this is 1 over p. Okay. So you can how many k of that? Okay, you can take this, and then notice. Right, so this p equals to 2 is your famous Euclidean. Sorry, p equals to 1 is your famous triangular inequality. So p equals 1 triangular inequality. And the p equals to 2, you can prove by Cauchy-Schwarz. Okay, so this is what I'm gonna to prove. Okay, so before we do this, and let me just dive into a proof. Okay, so proof. I will do it step by step, and once I need to use the Holder's theorem, then I will write down. Okay, so let's consider each term. So let's say this is p, and then you can write as ak plus bk, ak plus bk, p minus 1. So this is as you use the inequality, the triangular inequality on the first term. So you get this and this. Okay, and okay, so now we use a Holder's inequality. Okay, so Holder tell you that summation, let's say xk, yk, you take absolute value, well equals to summation of xk p 1 over p. I think it's times a summation of yk and k and q 1 over q, for which everything 1 over q plus 1 over q is 1. Okay. Okay, and at least p, yeah, okay. Yeah, okay. So this is the Holder's inequality. Yeah, so let's let me see. Oh, maybe in my proof that I don't actually need to require that p is integer. Okay. So actually p can be any positive number because at just greater than 1, because this power is well defined. Okay. Okay, so from this Holder's inequality that I can for this term, I think, let me see. Okay, I can combine these two terms. Okay, so I can combine these two terms. I get k, ak. So let's okay. So let's do the first term. Well, less or equal to summation ak and the p and the 1 over p. Okay, so now in this case, this is yk, right? So now I should take summation k, ak plus bk by p minus 1, but I need to times q, right? So I need to find a q. So q will determine by p. Okay, so I should times q and 1 over q. Okay, and also for bk. Okay, and then you just add the length. Okay, so you add then you get the original, you get your summation of AK plus BK to the power P. Well, less or equal to the total, right? You get summation of KAKP over P plus summation KBKP over P, and the summation of KAK plus BK, and P minus 1Q 1 over Q. Okay, so notice that since this 1 over P plus 1 over Q is 1, so I think P minus 1Q should be 1. Okay. Let me see. Yeah, right. So because this P minus 1 is 1 over Q, and right. So sorry. Let me see what's going on. Let me see. Sorry, I'm stupid. Let me just yeah, sorry, it's not 1, it's P. Okay, the reason is that let's see, you get this, right? And you divide by P, you get 1 over this. Right, so P minus 1 times Q is P. Sorry, I'm just stupid. Okay, so you have this. Okay, so you can plug into this. Okay, so you combine everything. Let me just do it step by step. So AK plus BK to the power P is less or equal to summation K AKP over P plus summation BKP K 1 over P. So you see these two terms are already correct, right? How about this term, right? So you get final summation K AK plus BK, right? So P minus 1Q is P, right? So you get P divided by Q, right? So P divided by Q is not sorry, I'm stupid. So this P and the 1 over Q. Okay, so you see these two terms are the same, right? Yeah. So you can these two terms are exactly the same. So you can just remove it, right? So you can just get AK plus BK P, and then your power is 1 minus 1 over Q. Well, less or equal to summation AK P K over P plus summation BK P K 1 over P, and using this is 1 over P, right? Okay, so this is K. So we get AK plus BK P or P less or equal to summation K AK P or P summation K BK P 1 over P. Nice. So this is our Minkowski inequality for discrete version. Okay, so for any real numbers greater than 1, satisfy this property. Okay, so discrete version. Let me just talking about another parallel version, which is this kind of. So every time you have a discrete inequality, which looks like summation, then you can try to do it for the continuous version. Okay, so we need some basic understanding. So suppose usually your f will be some function on a measurable space, and let's say you have measurable space. So or basically you can use the back measure, right? But let me just write some more formulas. Let's say X is a topological space, and then there is a sigma algebra on it. So basically, it's making measurable space, and then there's a measure on it. Okay, so measure on X. Okay, and then you can define let's say from X to let's say a real number or complex number. Then you can define LP, right? You can define LP space, which is all the functions. Should be measurable. So usually I use the back measurable, but you can use I can whatever you want, right? So f is measurable, and such that the f such that which is LP means that if you take absolute value and take p power, and you do d mu, then for your space X, this is finite. Okay, this is called LP space. famous in the quantum mechanics or the physics that people worry about like the L2, right? Because L2 space, quantum mechanics need the wave function to be normalizable, so people may care about L2 space. Okay, and then you can define LP known. So if F belongs to LP, so if F belongs to LP, then you can define LP known of P, which is FP or P. Okay, so this means integral of X, and sometimes I will neglect. Okay, so theorem, this is a famous theorem results that if F belongs to LP and G belongs to LP, then F plus G belongs to LP. Okay, fact. Okay, the reason, let me just write the reason. The reason is just the Minkowski. Okay, so now we can talk about the version. Okay, so the Minkowski theorem in LP space. Just like a triangular inequality. So F plus G P norm will less or equal to FP norm plus Q GP norm. Okay, and for any P greater than 1, of P is 1 is trivial. Okay, and the P less than 1, you can change this. Okay, P should be greater than 0. Yeah, otherwise that if P is 0, then you get 1, right? But it's not necessary that your whole space is compact. So maybe if you set P to 0, then it should blow up in general. Okay, so I think this one is the Minkowski. Okay, so let's write down the proof. So proof is exactly parallel. So let me just quickly do this. What should I do? Okay, so let's consider F plus G, P known to the P power. So it's F plus G, absolute value, P d mu. So you can write it as 2 terms, like you can write as 2 terms as I do it for a discrete version. So you just write happily in terms of 2 terms. And for each terms, you use a Holder's inequality. Okay. Holder. Okay, so I need to use the generalized version. Sorry, the continuous version for the Holder. So it should be F plus G, F times G absolute value is less or equal to F P or P d mu G Q d mu d mu over Q. Okay, or basically I can write it as a FG 1 norm is less or equal to FP norms and GQ norm. If 1 over P plus 1 over Q is 1. Okay, so let me just change the color because just for fun. Okay, so you get 2 terms. Okay, so these terms, so you now let me just use Holders, right? So I can use Holder. I think this is F to a P, d mu 1 over P, do the same thing, G to the P, d mu 1 over P. Okay, so these terms times this term, right? So you times F plus G, P minus 1, P. So you get I should get Q, right? But there originally has this. So let me just write it as let me just do this, right? So you get this term to the P, right? So Q, right? So you usually get this is Q, and 1, and 1 over Q. Right? Yeah. Okay. So exactly the same thing. Okay. So finally, these 2 terms are already what I have. I get this. This is both P. Okay. And these terms can be written as I think it's F plus G norm PP divided by F plus G P. Okay, the reason is that you get something which is you can also check this. I think here should be P, right? So this is the P known, right? But you need to times P, right? Because when I define P known, there's 1 over P, so this guy should be this. And this guy is 1 over Q, right? So 1 over Q is just 1 minus 1 over P. Okay, so you should able to just write as this. And the left hand, remember what is the left hand side, right? What is the left hand side? The left hand side is this, right? So you get F plus G and the PP norm, right? PP that's equal to F P plus G P times F plus G PP F plus GP. Okay, so all you need to do is just cancel, and then okay, so you get finally get F plus GP. That's equal to F to a P plus G to a P. Okay, so this is right. So very simple. So this is my proof for Minkowski. Okay, so we discussed the continuous version and the discrete version. That's all. Okay, so see you guys next videos. Hope you guys subscribe to my channel.